Okay, so the first uncertainty we're going to talk about is this idea of systematic error, systematic uncertainty. I'll use the words error and uncertainty and probably change them around quite a lot. The error is how much the experiment is wrong. Okay, Ross, put the ruler down. Put everyone down. You can copy down what I've got on the board when I start writing. So, how much the experiment is wrong and why was it wrong. The first one is going to be systematic uncertainty. Okay, and we'll write down what I mean by that, and we'll give a little definition of systematic uncertainty. Now you just need to be aware of what it is and be able to identify it in the experiment. Okay, so for example, the first one is going to be systematic uncertainty or error. You call it systematic uncertainty or error. Okay? Now, this error is, now if something is a systematic problem, a systematic failure, or a systematic error, it's something that happens over and over and over again. Something that's systematically happening to something, or systematically happening to a system, means it's there all the time and it's always happening. So a systematic error is something that's there the whole experiment. You can't really, you might be able to do something about it, but it's there and it affects all your results, every single one of them. Okay, so a systematic uncertainty or a systematic error is, this is an error which has affected or effected, I can never remember if it's effected or affected when you're writing down. An error which has affected all, what would you say?
Affect.
Affected this one. How do you know the difference?
Well, an effect to something and to affect something.
Okay, so an error which has affected all of your readings and is not always obvious to correct until you view your results. So a systematic error or uncertainty tends to be something that you try to do experiment as best you can. You've read the meters and everything as best you can. But for some reason, it's just affecting all your results, and you get these results that are all wrong. Every single one of your results is wrong. All your times are wrong, all your accelerations are wrong, and they're all wrong by the same amount. So systematically across your whole experiment, all your measurements have been wrong by a certain amount, the same amount every time. Now what we look for is, when we look at our graph, we can only really find out the systematic uncertainty from our graph. So we look at the graph of an experiment and we look at it and say, is that right? Or has there been an error throughout the whole experiment? Okay? Now, we'll do an example of that just to explain it. So an example of that could be, if you've got a graph, and the graph looks like this, okay? Let's say that is, say it's a velocity time graph, or we could say it's a load of things. Let's say it's a velocity time graph, and this is for an object down a slope. U equals 0. Okay, and it's just a sketch. I don't want a perfect diagram here. Now, what is wrong with this graph? Somebody tell me what you think's wrong with this graph. Alison, I know you're correct. So let's try and find somebody else. No offence. Let's find somebody else. Andy, what do you think? Why? Because of rest. So obviously, the graph's wrong. But for some reason, but if this is going down a slope, what else can you say about the motion of this object? Scott, what else can you say about the motion of the object? Sorry? It's getting quicker. Does that slope look normal for an object going down a slope? Does the slope of the graph, does the graph look normal for an object going down a slope? Mm-hmm. Apart from it not starting at 0, does it look normal? Yeah, so it's going to start off at a value, then accelerate down the slope at a constant acceleration. That is normal. That's what will happen. This is what is expected. However, the graph's wrong. The graph's wrong because it's not starting at 0. So you can say to yourself, we've got a systematic error here. Our graph is actually out by this amount here. this little amount here is an error. Because we think u should be 0. U should be 0. So this should be 0 to start with. So if this error was, say, 5 meters per second, then we know all our results are out by 5 meters per second. So what we could then do is take all the results that we have, so say we plotted this graph from a set of results, we could take all these results and we could minus 5 meters per second off them all to correct for the systematic uncertainty. Okay, so all the results are wrong. They are all 5 meters per second more than they should be. We can correct this by subtracting the 5 ms from all results. And what we're doing here is we are correcting for systematic uncertainty. So this would be correcting for systematic uncertainty. Okay, so you can see there that you might not have, you probably would be able to see this uncertainty from your table of results. You're not necessarily going to see it from your experiment. Because as far as you're concerned, the experiment's probably working fine. But you know the object started at rest at the top of the slope, and for some reason when you plot your graph, it's not doing that. So you've got some kind of systematic uncertainty in here. It might be that the apparatus is calibrated wrong. It might be that the apparatus is saying that it's 5 meters per second more than it should be. So to correct for this, you would subtract them all. But you have to be certain that there is a systematic uncertainty and not just inaccuracy in your readings. So systematic uncertainty is something that applies to all your readings, all your results, and it's something you can correct for once you've plotted a graph. Okay? So the actual, what actually says about systematic uncertainty in your learning outcomes is that you need to, there we go, distinguish between random uncertainties and recognised systematic effects. This would be a recognised systematic effect. And state that where a systematic effect is present, the mean value of the measurements will be offset from a true value of the physical quantity being measured. So what we're saying here is this is offset from the true value by 5 meters per second. And we can correct for that by subtracting 5 meters per second from the results. Okay? So that's the first one, that's systematic uncertainty.